Hello everyone, here is a brilliant question on the board and it has more than one choice correct. So requesting you to please post your opinion in the comment box which options are correct according to you. I am simplifying the things here on the board. This ring is fixed and it is uniformly charged. First of all, we'll determine the direction of the electric field in this plane at various points inside this space. Got it? So let us look at the center first. Once we know the direction of the electric field, we can easily use F is equal to QE and we can determine the direction of the force. So at the center, if we check carefully, due to these charges, the field will be radially like this. Now we take diametrically opposite charges, then due to them the field will be like this. If we consider few charges here, point charges here, due to them the field will be in this direction. Diametrically opposite charges, the field will be in this direction. I hope you can guess the field at the center of the ring will be 0. If we consider some element here, due to that the field will be like this. If we consider the diametrically opposite element, the field will be like this. All these fields will get nullified, will get cancelled. So we can write the electric field at the center of the ring is 0. Now let's consider some off center point. Suppose we consider a point here, this one. And now we want to determine the direction of the electric field at this point. The point lies in the plane of the ring itself. Can you guess where should be the electric field? What should be the direction of the electric field at this point? Let me know in the comment box. The correct answer would be the direction of the electric field at this point or this point or this point or any point inside this boundary will be always toward the center of the ring. That's an interesting result. I'm going to prove it. Suppose we consider small angle, very small angle d theta here, this angle. Now, due to this angle d theta, we can consider here some arc length, okay, and this we will consider as a point charge because d theta was a very small angle, so this arc length will be very small. This radius, let's say I'll call as r1. Due to this patch, due to this small charge, where should be the electric field? You know the result. Due to this charge, the electric field will be somewhere like this here. Do you agree? Now what we do, we extend these lines, this one and this one, and we consider the charge here. This radius we consider as r2. This angle should also be d theta. Due to this red element, where should be the electric field? Obviously, due to the red element, the electric field should be somewhere in this direction. I'll call that field as E2, and that field due to the black element, I'll call that as E1. Now, which is stronger, which is weak, or they have the equal magnitude? To obtain the data, what we can do, let us write the expression of E1 and E2. The E1 will be K Q1 by R1 square if we consider the charge here as Q1, and charge on this red element, this red line, we consider as Q2. Then E2 will be what? KQ2 by R2 square. Let's write the expression for E2 here. The ring is uniformly charged and the linear charge density of this ring we consider as the lambda. So what will be the Q1? The Q1 can be written as the lambda into R1 d theta. I hope you agree with that term. Lambda is the charge per unit length and R1 d theta is this length. So charge per unit length into length gives us the charge Q1. Got it? Similarly, we are writing the field here. So it should be equal to K. Q2 will be equal to what? Lambda R2 d theta. And here is R2 square. Done. If we compare the things, we can easily see K lambda d theta. K lambda d theta is present in both expression. This R1 and this square power is getting cancelled out. This R2 and this is getting cancelled out. So we can see that E is, if we consider this k lambda d theta, same data. So E is inversely proportional to the R. Smaller the distance, more will be the strength of the electric field. Got it? Since R1 is less as compared to R2, it indicates E1 is greater as compared to E2. So we got the result. The net electric field due to these two elements will be directed toward the center of the ring. And we can do for other pairs of the charges also. Suppose we consider some another angle d alpha here. So this angle will also be d alpha. Now due to this patch and this patch, figure out the direction of the electric field. Similarly, we consider some patch here. Due to this patch and this one, figure out the direction of electric field here. You'll observe one thing, that finally when you take the resultant for all those vectors, the resultant will be toward the center of the ring only. I can give you the quantitative idea. For this patch, the field will be here, and actually this will be stronger because the distance here is less. Now, for this patch, the field will be in this direction. For this patch, the field will be somewhere in this direction. For this patch, the field will be somewhere here in this direction. So when you take the resultant, you can see the net resultant will lie along the center. So we got the remarkable result. The point might be here, 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 here. For all these interior points, the electric field is along the center of the ring. Now we can answer all the options very easily. Number one, at the center of this ring, if we put a positively charged particle having the charge plus q, a small test charge is placed and the entire ring is positively charged, the net force on this charged particle will be 0. You remember that because here electric field was 0. Now if we displace it, the net force will be toward the center itself. If net force is toward the center, it means it will try to return back to its initial position. You displace this charge particle here, the net force will be toward the center, it will again come back, it will cross the center, it will go here, then its net force is again toward the center, it will go there again. This is the stable equilibrium position for the positively charged particle. Now what happens if we consider a negatively charged particle? We put a minus q charge, let's say once at the center. For this minus q charge, the net force will be 0 at the center. So it should be in some kind of equilibrium because the net force is 0. Now I displace the minus q, let's say here. We know that net electric field is toward the center of the ring. Electric field is toward the center of the ring, then the force on that minus q charge will be in the opposite direction of the electric field, because for force we know that F is equal to Q times E. When we put the negative charge here, force will be in the opposite direction of the electric field. So if this minus Q is released here, it experiences a net force toward the periphery of the ring. So it will keep on moving and it will hit the ring. So the equilibrium of this minus Q at the center has the nature of instability. Got it? This is in the unstable equilibrium. This charge at the center is in the stable equilibrium. You may note it down. Now, taking up the next part of the calculation, whatever points we considered on the previous screen, all those points were lying in the plane of the ring itself. But now for the next part, the ring lies like this and the point of discussion lies along the axis of the ring. You get it? Here is the center of the ring and the point has been taken here on the axis. I'm going to draw the diagram on the board. Suppose here is the ring. The front part is visible to us. The dotted part is behind the board like this. And the axis of the ring is like this. The point of observation is here. We consider this distance as x. The radius of the ring was given as r. How much is the net force on this charge? Since this is a positively charged ring, the minus q will be experiencing a force along the center of the ring like this. Explanation is pretty simple. If I consider here some small charge, this charge will exert a force in this direction on the minus q. This charge will exert a force on minus q in this direction. Net resultant will be along the center. And this we can do for all such small elements on the ring. Clear? Writing the expression of that, F. F will be equal to Q times electric field, which is equal to K Q X divided by R square plus X square power 3 by 2. I hope you remember the expression of the electric field due to a uniformly charged ring at the axis of the ring. Now our computation says that this x is pretty small as compared to the r. So I am taking the r outside. F will be equal to q k q x. Taking the r outside means r square has the power 3 by 2, and here will be 1 plus x square by r square power 3 by 2. Got it? Now this 2 is getting cancelled out. So F is K Q Q X divided by. We are considering that X is much small as compared to the R. This displacement was very small. So R is a greater term, X is a smaller term. So this term is almost negligible. So here in this bracket, we can consider the net data to be 1 only. So the remaining expression will look like this. Here we have proved that restoring force is proportional to that small displacement x. F is proportional to x, and this is the restoring force. Therefore, this particle has to perform the simple harmonic motion. And suppose if someone asks us what is the time period of this oscillation, that can also be proved. If this charged particle has the mass m, the time period will be 2 pi root m by this data, k q q by r cube, where that k is equal to 1 by 4 pi epsilon naught. So among the given 4 options, the 3 options are correct. I hope you have marked the correct options. Stay awesome. See you again.